Hey, this is Don from Padlock Technologies again with another video. This time, got a question on VPC, basically data center networking. What is VPC? Why and where you would use it, and some of the caveats that you got to consider when configuring VPC. So let's get down to the whiteboard here. This is going to be a whiteboard video, and then I'll probably do a quick lab real quick in another video, actually showing you what that looks like. So for VPC, if you haven't ever heard of it before, it's called Virtual Port Channel, right? And what this is basically another MLAG technique or multi-chassis link aggregation group, right? So you have your, lag, which is your normal port channel stuff, and you have a multi-chassis lag or multi-chassis link aggregation group, which means it spans multiple devices or multiple switches in your environment. So I'm gonna put MLAG here as well. So what this typically looks like is in the Catalyst world, you would say this was either Stackwise or Stackwise Virtual, depending on what devices you're using. Stackwise is normally used at the access layer, and then Stackwise Virtual is usually used either at the distribution and core layers or collapse core layer, right? So what VPC is like it's that, right? But you're doing it in the data center networking. And if you look at back in the day, they used to have like the 4500 series and the 6500 series had this technology called VSS, which is basically what VPC is, but there is a caveat there, and I'll explain with virtual port channel. There is something that's different than all the other multi-chassis uh, link aggregation techniques, right? There is one key difference there, and if you don't really pay attention to it, it will burn you when you configure VPC. So VPC, let's do the little drawing here. So we're going to have two pairs or a pair here. Sorry, not two pairs. All right, so you're gonna have Nexus switch one, so NXOS one, NXOS two. All right, and then let's say down at the bottom we'll have regular switches here. Now, looks eerily similar to like a cloth fabric, but this is not a cloth fabric design. So what you're going to have is link here, link here, link here, link here. Now, from the axis switches up is a single port channel. So this is going to be a single port channel here and a single port channel here. From the nexus switches down, you're going to have this, you're going to have a virtual port channel, but they're going to be separate devices, right? But they're going to look like one device from an L2 perspective. The other thing here that we need to actually discuss is you need two specific links. So you're going to need, I'm going to use different colors for these. You need your peer keep alive. So let's say peer keep alive, so PK, and then you have your peer link, which has to be a port channel. At least I would say be a port channel. You have your peer link here for your synchronization and stuff like that. Now on that port channel, the minute you say VCP peer link, it will turn on bridge assurance. So just know it'll tell you, hey, we're gonna turn on bridge assurance, and that's going to be syncing the L2 stuff as well, and keep bad things from happening. Um, the other thing is the peer link or the peer keep alive is to make sure the other peer is up. So this has to be some type of L3 link. And there's two ways you can configure it. You can use the management port if you want to by default when you configure VPC. When you do the pairing command or the peer destination, it will if you don't specify a VRF, it will always default to the management VRF, right? So this link here can be in either a separate VRF, or you could just use the default management VRF. Now, if you use the default management VRF, you may run into problems later on trying to remote into this box unless you're going to just remote to a SVI that's on the switch itself. But the management interface is usually for management traffic, and it's out of band management there. So once you have VPC set up, when you set up your virtual port channels, what actually ends up happening, and I'm gonna use blue for this, is this port here would be in, VCP 1, and say this port here is in VCP 1 as well, right? And then let's say this other port over here, just going to the other switch, is VCP 2, and this is in VPC 2. Now, to the downstream switches, it looks like, and I'll use white for this, it looks like one switch from an L2 perspective. All right, from an L2 perspective, it looks like one switch. That's why the spanning tree route has to be the same on both Nexus switches, so you don't run into problems from a spanning tree perspective, right? Now, other things that you can do is, now we're going to talk about the layer 3 issue. So from a layer 2 perspective, everything's all good, looks the same, right? From a layer 3 perspective, it's independent control planes. So that means box number 1 and box number 2 controls its own routing. So from a first hop redundancy protocol standpoint, you may configure switch 1 as the primary and switch 2 as the secondary. But if you use this command called peer gateway, both switches can respond to, any kind of request for traffic or something like that. So you use, most of the time, you're going to see VRRP because that's open standard. But if you use, HSRP, you can use that as well. What's going to happen when you use the peer gateway command is, let's say, again, this was the prime and this was the secondary. What happens is, if traffic goes to the secondary this way, it can send traffic upstream, right? Because it controls the routing, right? It has its own control plane there. So it doesn't kick it over to the primary and then the primary sends out. That doesn't even do that. So if the secondary does happen to answer, or the traffic does go over to the secondary, since the control plane is different on each box, it will go upstream based on its own routing table. Same thing here. So if traffic, I'll use a different one. I'll use green. If traffic happens to go this way, because from an HSRP perspective, the primary is going to answer, then obviously it'll go upstream to whatever router it needs to. Now, the problem with this, or where people get messed up at, is when you do BGP pairing or you do OSPF, what's going to end up happening is, since you have VLANs and SVIs on here, let's say you do OSPF, right? And you're just going to do OSPF on here, and you probably do BGP upstream if you're going directly to routers. If not, it'll probably be OSPF as well. What ends up happening is, when you do your show show IP OSPF neighbors, you will see a neighbor under each SVI that you activate, right? So you will end up seeing, I'm peering with Nexus 2 on whatever SVIs you have here. And you're like, why am I doing that? Because of this VCP peer link is synchronizing their data. So as soon as you put an IP address on one side, an IP address on the other side, activate EIGRP, you're going to see that neighbor adjacency happen. So you just got to be careful of that neighbor adjacency, so you know how traffic can, where the traffic is coming from. What you can do, if you wanted to, you could potentially prune the VLANs from the VCP peer link. Most people do not. They don't do that. But it doesn't. You run into problems when you have a situation like, give you an example, and I've seen this happen. You run into situations. Let's say you have a router up here, and then it goes to both switches. Well, if this is not a port channel, that's not a port channel. What ends up happening is, traffic can go, it can see from a routing perspective, it could potentially cause a loop, right? Because it'll come back, the traffic will go down the switch 2. Switch 2 will say, okay, I got those routes here. And then when the routes get shown into Nexus 1, it could send that route right back to the same. So you could potentially run into loops if you do this. That's why it's better to run port channels on all your devices instead of being single connections. Now, if you do have a single connection, is an orphan port, because technically, let's say you had something else over on this side connected in. Well, it's only one connection, so technically, and I know I said technically a lot. With this switch goes down, this whole thing is abandoned. There's no other way for it to get out, and that's basically what an orphan port is. So where would you see this? Well, a couple things. You're definitely going to see this in the data center, right? Collapsed core design, or namely collapsed core, right? Because if you're doing something like fabric, which is cloth fabric, you would see VPCs at the leaf switches, and they would connect to each individual spine, right? You're not really going to see VPC at the core switches in the fabric, because that's never configured VPC on the spine switches. That's not what they're there for. Um, they're there for more links, more ways to get to other VTEPs, as they call them, leaf switches. And then the VTEPs is for port capacity, when you want to add more ports, right? You also have a design called back-to-back VPC, which is you'll have a VPC up top of above this, and then there'll be VPC on the bottom. Um, some people use that design, some people don't, but you're really going to see this in your data center network, usually at the core or distribution layer. So that's VPC in a nutshell, right? I know it was a real brief explanation. Next video is going to be a lab showing you the exact design, and it's just going to be one single VPC, one simple VPC domain, and then I'll show you from an L2 perspective what that looks like. And I may add some routing in there as well, so it makes more sense of how it gets, how you can get out, how the control planes are different on each box, and all that good stuff. So again, this is Don from Padlock Technologies. Hopefully this answered your question. I hope this video was informative. If you have any questions, there's going to be a video bumper at the end with an email address of where to send your questions. Thank you, and have a nice day.